Okay, so in a previous video, we talked about the Jordan-Wigner transformation, which we use to map spin operators into spinless fermions. Now we are going to talk about the Holstein Primakoff um, transformation, which we use now to map spin operators into boson operators. Okay, well, let's recall boson operators. So what we know about boson operators is that they satisfy the commutation relations. So B with B dagger is 1. Here we are talking about a lattice system, so we distinguish the sites. So B, J, and BK dagger will be 1 if J and K are equal. We also know that two annihilation operators commute, no matter which sides they are, and creation operators as well. So what is the importance of these commutation relations? Well, one important thing is that what we see from here is that the order doesn't matter. The bosonic created operators, they commute. So the order in which we are going to create the bosons does not matter. And very important, you see that now B dagger square has no reason to vanish, as it did happen in the cases that we studied before for fermions. Has no reason to vanish. It does not. Now, what this commutator is telling us is simply that this is true. So doesn't have to vanish, which means that we can have as many bosons as we want on each side. Okay, so this is what is true for real bosons, what we are familiar with. But now comes our transformation, this Holstein Primakoff transformation, where we are going to move from spins into bosonic operators. How do we do that? Now comes the transformation. We are going to connect the raising spin operators with creation operators. Very good. But with something else in this story, where here we have n the number of the number operator, and same thing for the lowering spin operator. We again have this square root, so you see the order matters. You see now that the number operator came before the annihilation operator, and SZ connected with the number operator, minus here a constant. Okay, so this is what we have. This is the Holstein Primakoff transformation. Okay, so you see that we are not dealing with the real normal operators. You see that this mapping has a constraint from these square roots. We see that it works. The map is exact. It works very well, provided these number operators will be the occupation will be smaller or equal to 2s. Okay, so it's not any number of bosons per site, but we have now this constraint. Okay, what is the advantage of this transformation? One of the advantages is exactly that it provides us an easy or direct way to think or to study semi-classical limit. And the semi-classical limit is the limit that we have when S is very large, moving towards the classical limit. And so in this case, when S is very large, you see that that square root we can write this square root as in terms of this expansion. So this is the dominant term because we are thinking about this scenario where S is so large that it's much larger. And so we are thinking about a scenario where this expansion is coming from a scenario where this 2S is much larger than this expectation value. So you see that this is the dominant term, which is just a constant. And then comes the contributions from the operator. So this provides a very good or direct way to study the semi-classical limit. Okay, now we move to the case of spin half, because that's what we've been studying. We've been studying spin half models. So in the case of spin half models, well, this discussion about semi-classical limit does not apply. So we'll now be talking about spin half. And you see that we now have the constraint for this occupation, this bosonic occupation, is 0 or 1. This relationship tells us that the occupation has to be smaller or equal to 1. So we are now in this scenario. Okay. So this is a very special kind of boson, and we call it hardcore bosons. Okay. So we are dealing here with hardcore bosons, which means on each side we either, and so on each side we either have a boson or we do not have. And so it's occupied or empty. And that's it. Okay, so very special kind of bosons. Okay, we do this transformation following what we wrote here. But now for spins half, and you see, well, the transformation looks very simple. The raising operator just becomes the creation operator, the creation bosonic operator. The lowering operator is the annihilation, and SZ is the number operator with a constant. Okay, so coming back to the case of the XXZ model in one dimension, as we were writing before, with this transformation, we can then write this Hamiltonian in terms of bosons, but very special kind of bosons. They are hardcore bosons, so we can write it like this. So here we have neighboring sites. If we are talking about the one-dimensional XXZ model with neighboring couplings, and if we are talking about open boundary conditions, we go up to L minus 1, L meaning the number of sites. And the contribution from the ZZ term, what we call the easy interaction, is involves the number of operators now, neighbors as well. Okay, so this becomes our Hamiltonian. For those who watch the movie about the Jordan-Wigner transformation, say, oh, this looks very much like the Hamiltonian that we obtained using that language of spinless fermions. And you may be tempted, but don't do that. You may be tempted to say, oh, okay, so playing with these hardcore bosons, again, I can separate, I can identify what is interacting from what is non-interact. This is not true. Okay, be very careful because we are talking about hardcore bosons. So hardcore bosons, they have this special constraint here. Now, hardcore bosons have this special constraint that we cannot put parentheses here, no? That we cannot remove two bosons or create two bosons on the same site because we can, the maximum occupation is one. So this constraint, what this implies is that we have on one side a very strong, an infinite strong interaction. And so this constraint implies that we have on-site interaction, a very strong on-site interaction, repulsive interaction that does not allow more than one boson to occupy that site. So this means that the theory becomes very complicated. We don't see that in the special scenario of one dimension, because if you use the rule is always use the Jordan-Wigner transformation. Go back to spinless fermions. And then check the terms that you have in your Hamiltonian. In this one-dimensional case, which is very particular, you will see that, okay, this hopping term becomes the same hopping term that we saw in the language of spinless fermions, which we said, oh, this is bilinear, non-interacting term associated with quadratic Hamiltonians. This is true in 1D, which is very particular. If you pick that hopping term with hardcore bosons, okay, we are talking here about hardcore bosons, but in 2 dimension, okay, so let me write here, instead of J, let me put K, because now I'm thinking about 2 dimension, and I'm thinking about, could be again, neighboring couplings. But in 2 dimension, if you do the Jordan-Wigner transformation, you will see that this is very complicated Hamiltonian. It's not just bilinear. It's not bilinear. It's not non-interacting in spinless fermions. Okay, so you will see that this is a more complicated term. Okay, all that to say, hardcore bosons are very special. Okay, so this is not the way to distinguish interacting from non-interacting terms. You can, if you want to distinguish that, if you want to determine whether your Hamiltonian is quadratic, whether your Hamiltonian is non-interacting, so all this is like synonyms. If you want to determine whether your Hamiltonian is quadratic, whether your Hamiltonian is non-interacting, and therefore whether your Hamiltonian is integrable, you should go to spinless fermions, Jordan-Wigner transformation. Okay, now all this because with spins half, we are, and when we did this transformation, we were playing with hardcore bosons, which are special kinds of, which is very special scenario. If we talk about real bosons, then yes. If we're talking about real bosons, those hopping terms, it doesn't matter if we are talking about 1D, 2D, 3D, doesn't matter. This is really bilinear. This is really quadratic. Okay, so this is really non-interacting. When we are talking about real bosons or when we are talking about fermions, as we said before. The special case here is hardcore. So hardcore, careful with this term. This is not necessarily a non-interacting term. It is in one dimension, but not in higher dimension. Okay, so I hope this was clear, and this is the end of this video.